To remind you where we are looking at a series of memory allocations and talking about how every single process in your computer has a page table. And that page table is private to each process, and the page table is essentially a series of pointers. And this series of pointers is going to help us manage how we allocate our physical RAM and share it between lots of different processes. So to do that, we're going through and we're looking at how one process is making a number of memory requests. Or actually, sorry, 3 processes are making a number of memory requests. And where we left off is we left off having done the first 3 requests. We made 3 malloc requests. We mallocked A from process 1. We added A to the process 1 page table. And that malloc was 3 pages long. It was 3 times 4096. Each page has 496 bytes on it. Process B allocated 5 pages worth of memory. And you can see its page table now points to the RAM in the center. And step 3 was process 1 then allocated 2 more pages. So at this point, we are on step 4. And step 4 on our sheet says that process 3 exits. So this is something that's really cool. Because one thing that I heard a lot of people come out of 225 with was, what happens if you leak memory in your process? Does it just stay leaked forever? How does the operating system actually clean it up? So if you malloc memory and you never free memory, it's going to be stuck in your page table forever. But now when process 3 exits, what happens to everything that's allocated in process 3's page table? Do we ever need it again once the process exits? No. So we never need process 3's memory again. So as soon as a process exits, no matter if you freed the memory or not, all of your memory simply gets cleaned up by the operating system. So once process 3 exits, its entire page table is done, and the system can now say, hey, this memory that we previously allocated is now free again. We can reuse that for another process. So step 4 is we clear out process 3, it's exited, everything that was allocated to it in its page table is now reallocated back to the operating system to assign to other processes. Awesome. So page tables will help us kind of clean up after a process. We know exactly what resource the process used, and we can go ahead and clean it up. Yeah. Oh, will block C move up, or will it stay there? Why? Should we waste time in moving block C up? Yeah, so actually let's go to the next step and see what happens as we move the system. In general, we're not going to move anything inside memory unless we absolutely have to, because moving things in memory takes time. It's slow. So we want computers to be as fast as possible. So it's okay that the memory has a hole in the middle right now. And we're going to, in next week, we'll actually talk about how that's a form of fragmentation. So fragmentation will hurt our system. Yeah. Yeah, because the process is exited. It's not that we're just freeing B. The process 3 is exited. It's returned from main. It's done. So it's completely gone. Cool. So step 5, process 2. Hey, we've got a new process that came along, and it wants 4 pages of memory. So I'm going to go ahead and on its page table allocate 4 pages of memory. And now this variable D is equal to 1000 as well. So we have 3 different processes that all thinks it has memory address 1000, because that's address 1000, all of its virtual page tables. And now I have a question. There's no right answer here. But we as operating system designers can choose, where do we want to stick variable D in memory? Where's actual storage for variable D in RAM? Do we want to stick it right at memory address 3000? Or do we want to stick it below where we have the data for C? What do you want to do? Yeah. Yeah, we can just stick it in between because it looks nice. We can go ahead and reuse that memory. It doesn't matter where we choose to stick it. It's just RAM. All the RAM's the same. Remind me of your name one last time. Jackson said, I just want to go ahead and reuse this RAM. So because Jackson said so, we're going to go ahead and point this page to here, this page to here, this page to here, and this page to here. So something actually really interesting has just happened. Let's say I try and access data inside of D without actually writing to it first. What data is in RAM where variable D is at right now? Yeah. Yeah, whatever was left over from B is still stuck in that RAM. So D is going to have all those values for B in there. So when we talk about garbage data, this is exactly how garbage data gets to RAM. So in modern systems, when you actually give it to another process, you actually usually zero out the RAM so you don't leak data between processes. So in modern systems, we have things to protect it from like leaking private information. But as a general principle, but within the same process, if you reuse memory, you don't zero it out. So this is kind of where garbage values actually come from. So the next step is step 6. Now process 2 has allocated 5 more blocks of memory. So now we have variable E, and I'm going to go ahead and try and change the color ring. All right, so now we have variable E, and E is 5 blocks long. So 1, 2, 3, 4, 5. So the memory address for E is 1,000, 2,000, 3,000, 4,000, 5,000. So E has the pointer 5,000. So if we look at what the value of E is going to have the memory address 5,000. And now we have another decision. Do we want to put all these blocks sequentially in memory? Or do we want to divide it up to not leave holes in our RAM? And there are advantages and disadvantages to either one, and your operating system might do either of those two. So there's no wrong answer here. What do we want to do as designers? Do we want to put the first block of memory right in that little tiny hole, because there's a hole of free memory right here? Or do we want to skip the hole and just allocate all 5 blocks contiguously? Skip it? Whose team skipped the hole? Whose team used the hole? Okay, I think team skip the hole 1. So I'm going to say that as designers, we're going to say that this now maps to this block of RAM, this maps to this block of RAM, this block of RAM, this page of RAM, and this page of RAM. So we skipped the hole. Now we have 2 holes left in our RAM, right? We've got a hole right in the middle and a hole right at the end. And now, step 7, we have a new command, realloc. So realloc is the way that we can increase the size of memory we've already allocated. And realloc is a time that we can actually reassign where the memory is pointed to. So realloc says, I want to reallocate where the size of A, and I want to change the size of A to 5 times 4096. So A's right now taking up 3 blocks, and A has to be a contiguous set of memory. So what we cannot do is we can't just expand A where it's currently at. Because if we expand A where it's currently at, we're moving into C's memory, right? A can't become 5 blocks where it's currently at because C's after that spot, right? So instead, we have to move where A is in memory. So we have to say, we can't have A here in this part of virtual page table anymore. Instead, we need 5 continuous blocks of memory. So I'm going to go ahead and stick it down here. So A, which used to have the address 1000, now has the address 6000. So now in process 1, if we look at what the address of A is, it's address 6000. And now we've got to decide where is the pointers to the actual data. So even though we move the position of A in RAM, where does the pointer of the first page actually go to? Do we have to move any data around inside of memory, inside of the actual RAM? Because where's the data that was in the first page of A? Where is it in RAM? Still there, still at the first spot in RAM, right? So we can, even though we're moving where it looks like it is in memory, in reality, we only have to update a few pointers. So A points to here, second page points up here, third page points up here. Ooh, but we need 2 new pages. So where does the fourth page have to point to? One of those holes, right? So the fourth page of A is actually located in RAM at address 7000. The fifth page is actually located physically in RAM at F1000. So this is how our system manages memory. As we call malloc, every time we need a new page, the operating system assigns a page to our process. And that process page then gets mapped to memory somewhere, because none of the data is actually stored in the page table. Page tables are just a series of pointers. The actual data is only stored in RAM. And the operating system is going to manage the RAM and assign processes pages in RAM to place their data. And the abstraction we do that is through a page table. And these addresses of where it's actually located in memory, in our virtual page table, these are our virtual memory addresses. And notice how 3 different processes all had memory address 1000. That's because these are virtual memory addresses private to each process, and they're not the physical memory addresses of the RAM itself. So this is really cool. We have a way to actually share all of the memory in our computer between lots of different processes and keep processes out from accessing other people's memory. Any questions on the page table? So if not, yeah. What exactly happens when a page table is erased, like when a process exits? It simply looks through all the pointers that where the page table we're pointing to and marks that area of RAM as free now. Yeah, is the value still in RAM? Probably. Yeah, if we do nothing, the values are still in RAM. In a modern system, we do zero it out just for privacy reasons. But in reality, it's still there until we do zeros. Yeah. Awesome. Any other questions? If not, I have a couple questions for you. So first, can we meet all of the allocation requests that were made? Were we successful in allowing this series of processes to run? Yeah. Yes. Everyone got all the memory requested. And this wouldn't have happened if we couldn't actually fill up those holes. Because remember that last request, we actually used up every bit of RAM we had on this system. And this wouldn't have happened, or we wouldn't have been able to allocate this in RAM if we weren't able to use the holes up, if we didn't have different pointers to different areas of RAM. So from the process perspective, the process 1 thinks that A is 5 pages worth of contiguous memory. In reality, we've actually stashed the memory that A is in all across our RAM. So even though it got a little complicated, we were able to satisfy all the requests. And the second question is, we've talked about lots of different storage mechanisms. Should we be limited to just RAM? Or where else can we store data on a system? In fact, where does all of our data originally come from when we turn on our computer? Say what? It eventually goes to the CPU, but when your computer is without power, the CPU doesn't have any data in it. Yeah, Matt? Yeah, it comes from storage. So, no. Let's also map pages to our storage. So we don't always want to just necessarily say our data is in RAM somewhere. We might be able to allocate memory on our virtual page table and say that that memory, that data is actually stored on disk. So if we have a really, really large file, we may not be reading that entire file. We may want to allocate enough memory for it, but there's no reason to put it in RAM if we don't have to. We only need to put a data in RAM that we need to actually work with. Yeah? Does your computer get slower when you have less space on it? That's probably an unrelated issue, but if you see that your computer gets slower when you have lots of apps open, this is what's happening when you have lots of apps open. So if you literally have like 1,800 Chrome tabs open and a bunch of other stuff going, you may actually not have enough RAM to keep everything in memory, so it might use the disk as a temporary storage of RAM. As your hard drive fills up, I think that problem is more to deal with, like, you've got lots of small blocks all over your hard drive, so it has to jump around to actually find all your data. So that's a different form of fragmentation, but very similar principle. So that's awesome. Cool. Any other questions? That's a great one. All right. Let me know if I'm missing you, because this room is strange. So what are some advantages? Why do we care about a virtual memory system? Just to kind of summarize what we've talked about. Why do we care about this? Yeah, Aaron? Security, yeah. So definitely one huge advantage is security. So the virtual memory protects processes from reading the memory of other processes. Yeah, so because you can only access virtual memory addresses and you have to go through your page table to find out where that virtual memory address points to in RAM, you can't just access an arbitrary location in your system's RAM. So I can't access your data because I don't have a pointer to your data because you have your own private virtual page table that has your data in it. I have my private virtual page table, and I can only access things that I have pointers to. So security is a major reason. We love a virtual page, or we love virtual memory because of the security it provides. Why else do we love virtual memory? Yeah. Oh yeah, so we can have large contiguous blocks. Yeah, so we can have large blocks of contiguous memory. Even if the RAM does not have a large block, a large free block. So we saw this in the very end of the example that we did just prior, where we reallocated A to make A 5 blocks long. We didn't have 5 blocks free in memory, but we were able to do that even though it wasn't possible with the RAM because of the virtual page table abstraction. So we can have pointers to different spots in RAM for different parts of our data. So from the process's point of view, it looks like we have a whole 5 blocks of contiguous data. The addresses aren't split up. It's one big block. But once we follow the pointers, we find out that it's really 5 separate blocks that we call pages. Cool, and very last, so there's one more really big advantage. Yeah? We can split data up by processes. I agree that's an advantage. I'm going to put that under security. That is essentially what we've done with security. Let's split by processes. Were you else thinking something else?
Yeah, so it's simpler to develop things on.
Simpler.
As a developer, you don't have to worry about RAM and how things are allocated. You can just always say, I want these 4 blocks together and whatnot.
Yeah, it's an abstraction. Yeah, I like it. It's kind of simple to develop. I didn't even think of that one, but it's a simple API to RAM. It's kind of like a bonus one. We've got a simple API to RAM. We don't have to think about all these details. We just say we need 8 blocks of memory. The system gives us 8 blocks of memory. We don't care where it's stored. We know it's, from our perspective, it's a continuous chunk of 8 blocks of memory. Yeah, the API is really simple. It's dumb easy to use. I love it. All right, any other thoughts on what we love about virtual memory? Why is this the thing that's been used for 50 years? The last real advantage, I'd say, is something I've only alluded to, which is this idea that we have external storage. So we can extend our RAM to all storage. So we can allocate just massive chunks of data, even if we don't have that much RAM. So one example, I won't run this code, but in o5.c, I printed out what the beginning of the array is and the end of our array in the example that we did at the beginning of class on Tuesday. And this allocation ends up being, if I set size equal to 40,000, this allocation is 10 gigabytes big. 10 gigabytes is more than the 8 gigabytes of memory in this computer right here. So what I'm able to do is I'm actually able to allocate more memory than I actually have RAM because I can use storage. So I can say, okay, I'm going to allocate this huge block of memory. Some of that memory is going to get thrown off to my hard disk. Awesome. So any questions about virtual memory? So the thing I want to finish up this lecture 5 with is looking at a, we've looked at this program, is looking at a final sample program. And I want to have here, I'm going to now just focus on just one process virtual page table, but I also want to look at pages that are on disk. I want to go through an example with you of how a real program might run and how we interact with memory. So what we do is, in your disk spaces, disk data is also divided up into pages. So when you have this idea of inodes or anything like that, those point to actual pages on disk, and those are indexed from 0 to however large your disk is, just like your RAM is indexed. And just like RAM, you can stick things in different holes. You can do the exact same thing with hard disks. There's a slightly different system to do it. But all of this is handled by your file system. And from our view, as application developers, our hard drive just has a whole bunch of data on it. And I've given some random indexes, starting with, of course, CS240, because 240. And we might have our program code located on disk at page 240. And our program might be several bytes wide, or several pages wide, sorry. And then we might have, like for MP2, we have a hidden image hidden inside a PNG. And that takes up 3 blocks of data on our hard drive. So we have a bunch of different files on our hard drive at particular block locations or page locations on our hard drive. And I want to go through a small little program. So the first thing we might do when we run our program is to simply start to type /program code, or whatever, a.out, whatever our program's called. Whenever we start to run a process, the first thing that a system's going to do is it's going to go ahead and have our page table point to all of the pages of our actual program. So we have now allocated 5 blocks on process 1 virtual page table, and I've made that allocation. I said, I'm going to put all of my program code into memory. And to do that, I'm initially just going to give it a virtual memory address. And that virtual memory simply points to my storage, points to my hard drive. And then I've loaded the program. When I actually need to run the program code, that's the only time I need to actually load that data into RAM. So in step 2, I'm going to say, oh, I actually need page, I stuck in page 2. I need pages 2 data on my CPU. So the CPU can't access the storage. So what happens is page 2, we update the pointer, go ahead and load it into RAM, and copy the data. So we only load the first page of our program code into memory the moment that we need the program code to actually run on our CPU. So we don't, right now, program code page 2, 3, 4, and 5 have a pointer in our virtual page table, but it hasn't been accessed. It doesn't need to be used by the CPU, so we don't need to load it into RAM. So we don't load our entire program into RAM when we launch it up. We only load what we actually need to access the CPU. And then as part of this step 2, this first page of data says I want to make an allocation request of 4,000 bytes. So I'm going to go ahead and maybe have a heap right here. So this is going to be my program's heap. And in my program's heap, I'm going to allocate a page that involves 4,000 bytes. And that heap, we can go ahead and point to RAM. So in the second block of RAM is going to be our heap data. So our virtual page table now has both the program code, and right below the program code, it has our heap. Our heap has an allocation of 4,000 bytes. Now, we need to run program code page 2. So we've ran through a whole set of instructions. Remember, as we talked about in the CPU, we have a bunch of code, a bunch of object code, a bunch of assembly code that the CPU runs from one line to the next. We looked at running a sample program and seeing how the program counter just increments, runs through the code. Once we've ran through an entire page worth of code, an entire 4,096 bytes worth of code, we have to load in the next 4,096 bytes of code. So as soon as that happens, we'll go ahead and say we're going to need to load page 2 into RAM. So we're going to go ahead and load page 2 into the next free block of RAM. And of course, when we load it in, we actually do have to copy the data from storage, because that's where the actual data is on disk. So we copy the data from disk into RAM only at that time when we're about ready to use it. Then we need to malloc 10,000 bytes. So when we malloc 10,000 bytes, that means we need an additional 10,000 bytes on our heap. So usually we do allocations in terms of pages. So now our heap expands to 4 segments. So what actually, so I made a slight error in the sense of I put something in RAM that shouldn't have actually gone in RAM. Because when we did the malloc on step 2, did we actually access the data in malloc? Not necessarily, right? So I'm going to update step 2 to fix my mistake I made up here and say malloc 4,000 and access it. So if you want to fix your step 2 and say and access it, that will make it technically correct. because we had to allocate 4,000 and access it. So we actually accessed that memory, so we need it in the RAM. Here in step 3, I'm going to say we malloc 10,000 and not access it. So if we don't access that 10,000 bytes of RAM, if we never actually have the CPU use that data, is there any reason that data has to be in RAM? No, right? We can malloc the data. We can say, hey, operating system, we're going to need 10,000 bytes more of data. The operating system is going to say, okay, I've allocated you, I've expanded your heap, I've allocated this memory to your process. But it doesn't need to be in our RAM until we actually use it. So it's going to be an entry in our virtual page table, but it doesn't get into RAM until we actually use it. Third thing we might do, or second thing in step 3, we might open the image file. When we open the image file, we need to actually have some data inside of RAM, inside of our virtual page table that points to the image file. So same idea here. In our virtual, so when we open the image, we're going to load the image into our virtual page table by having pointers that point to it in storage. So all of the data our program is going to access, it's going to get a memory address on our virtual page table. And when we access the data, it's going to actually be put into RAM. I'm not going to go through the entire example, but I do want to go through the last part of this step, which is read all of the image. So if we read all of the image, we now need our page 12 to be actually in RAM. So I might go ahead and put page 12 in RAM here. And then I'm going to read the next part of the data. I need to read the second page of my hidden image. We've got a problem here, right? What problem am I running into that we need to read that second page of the hidden image? Yeah, what's going on? Yeah, I'm out of RAM. How do I fix it? Any thought? Yeah. Download more RAM? Oh, I wish there was a website I could just download RAM. That would be amazing. So unfortunately, RAM is a physical component in your computer, so you can't just download more of it. You could go throw another chip in there. Yeah, Aaron? You can free up more RAM or you swap. I'm going to summarize this as, can we just kick something that's in RAM out of there? Like, what's in our first chunk of RAM right now? What was it? Yeah, Matt? Yeah, the first set of instructions. We're done with that first part of the program code. We might jump back to it later, but if we jump back to it later, we can load it in again. We can say, hey, whatever's in this RAM, you're kicked out, you're evicted. And this is actually what exactly happens. We call this page eviction. That we run out of space, we have to evict something from RAM. So we have to decide which page we're going to kick out of RAM to make space for new data. And for something like the program code is going to be marked with a read-only tag. So kicking that out of RAM is pretty easy because all we have to do is update the pointer back to where it was on disk. So we know what the data was in RAM. We spent the time copying it. We needed to copy to run it. But as soon as we are done with it, or as soon as it hasn't been used in a while, we can go ahead and evict it and say, hey, the data's on disk again. If you need the data, just go get it from disk. So this example was here to kind of demonstrate the fact that eventually you're going to run out of RAM, and eventually we have to think about what happens next. And what happens next is the idea of how do we decide how to evict pages? How do we kick pages out of their home inside of RAM? Any questions on this? Yeah. Yeah, so how does it keep track of like what's free in RAM? Where does it store the parts that, I mean, so it keeps track of it in each process, a page table. Yeah, so everything that I put a square around here is going to be a page that has a valid entry into it. So it is data your program can access even if it's not in RAM right now. So as soon as you call a malloc, as soon as you open a file, as soon as you do anything to access data, we're going to map that data to a virtual page and leave a pointer to where that data is at. Either that it's in memory or that it's somewhere else. Yeah. So like this heap, like this, so this page right here is part of our heap, right? But we've never actually accessed it at this point. So the pointer is probably going to basically, I'm actually not sure on the like how x86 represents this, so I'm not sure the technical specification on this. But I suspect it's going to have a pointer to like null or somewhere that says this page has nothing on it right now. If you need to access it, go ahead and initialize it into RAM somewhere. Because the operating, like our job as systems programmers is to be as lazy as possible and make the CPU do as little work as possible. Because we don't want to waste time doing anything we don't have to do on the computer. So if we don't have to copy data, we don't want to copy data. If we don't have to evict a page, we're not going to evict a page. We're only going to evict a page once the memory is completely full. Does that kind of answer your question? Cool. Yeah. Can we extend it to storage? Unfortunately not, because the only thing the CPU can access is the RAM. So eventually, everything we're dealing with, anything that's actually running, that we actually are accessing, has to be in RAM. So we can't just start accessing things in storage from the CPU. So for the CPU to work on our data, the data has to be in RAM. So every time we get new data that we have to work on, either new program code, new files, new memory, we have to stick in RAM. So there's no connection between, the connection between the CPU and the storage exists through RAM. Okay, so I have a couple, yeah.
So in the second line, you have malloc of 4,000.
Yeah.
So how much thought do we have to put into numbers like it could be 4,096 or like, you know what I mean? Like how much thought do we have to put into putting in the right numbers or things like that?
So as a programmer, don't think about it. But as a system designer, the memory only gives us, the system only gives us chunks of 4,096 bytes. So if we did a malloc of 8, we're still going to get an entire page for our heap. So basically at a system level, we only think about things in pages. At a programmer's level, you're actually an MP3, you're going to see how you actually manage the individual malloc to memory. So don't worry about kind of being on page boundaries or anything like that as a programmer. This is just how the system actually does things. Yeah? Yeah, in the page table, if your data is on disk, the page table is going to have a pointer that points to where the data is on disk. So pages are a feature of the operating system. So when the operating system gets a request for your program to access a page that's on disk, what the operating system is going to do is it's going to say, hey, load this disk page into RAM, and then work on this data. Yes, the page table basically just tells us where we can find data. And if we actually have to use the data on the CPU, If it's not in RAM, we have to put it in RAM.
So is there like addresses for like the entire disk?
Yeah, your entire disk is divided up into pages, and you can index any page on your disk.
And is that for like staff and RAM addresses?
So the disk addresses are completely separate than memory addresses.
Okay, then like how's the page table distinguished like those two?
So I'm going to guess there's probably a bit that says, is this present in memory or is this not present? And in fact, I know there's a bit. It's called the present bit or the p bit.
Okay, so this is something that the operating system has full like complete freedom to decide.
It's something that the instruction set architecture defines. So as this gets very nitty gritty, but the operating system actually implements some of these things. But because we want it so fast, we actually do a lot of this in hardware. So the ISA, the instruction set architecture, defines how the page tables are laid out, so that some of this process that we're talking about is actually done entirely in hardware without having to touch the operating system. But in theory, if this wasn't implemented in hardware, the operating system would have complete control of that. So I don't want to lie to you completely and say the operating system has control of it, because some of it is done in hardware. But the reality of it is this abstraction is something that's been built over 50 years. And so now we've optimized just this to the nth degree. This whole idea is super optimized. Pages actually move into caches. There's a ton of details that we're skipping over to give you the high level picture. This is a whole super optimized process nowadays. So I have just two final questions for you. So the first question is, I have a disk image and it has a hidden image on it. How big is our hidden image? What are possible file sizes for hidden image? So how many pages is hidden image.png taking up on our disk? It's taking up 3 pages. So if this hidden image was able to be fit in 2 pages, would it actually take up 3 pages? No. So the size is going to be greater than 2 pages of data. But as we point to things on disk, we can only point to pages of data. So if you think about a notebook, if something's on page 1 of the notebook, that's great. If something's on page 2 of the notebook, that's great. But if your chapter ends halfway through page 3, the rest of your chapter page on a traditional book is empty. And that's how disk storage works as well. So if we know the hidden image.png is 3 pages large, we know the actual number of bytes in that file is somewhere greater than 2 pages and somewhere less than or equal to 3 pages of data. So that means the actual possible file size is going to be somewhere between 8192, which plus 1 bytes. So this is 2 to the 12th times 2. So we know each page contains 2 to the 12th data. We know each, or maybe I'll even write it as 4 kilobytes. We know each page is 4 kilobytes. So we know it's at least 8192 plus 1 bytes, or 8193. And it can be all the way up to 4 kilobytes times 3. So that's going to be 12 kilobytes. Or if we multiply this out, that's going to be 12,288. So the actual bytes that a PNG takes up is somewhere between 8 kilobytes plus 1 and 12 kilobytes. That's a range of possible file sizes for that file. But because we're allocating everything in pages, we're losing a little bit of space on a hard drive on what doesn't completely fill up the last page of the file. So this is a form of fragmentation, a topic that we're going to talk about next week. The idea that we're actually giving up a little bit of space to simplify our lives. That we're organizing everything into these pages that we can number, we can refer to. But in reality, there may be a little bit of space, depending on how big the file actually is, that's going completely unused because of the way that we designed our system. Same idea, we can look at program code. That takes up 5 pages. So that means it's somewhere between, it's got to be greater than 4 pages and less than or equal to 5 pages of data. So it's going to be somewhere in this range. And then what's the size of the heap immediately before the program ends? So we did allocate the entire heap. The entire heap's going to have the exact same problem as paged on disk. So we have allocated 4,000 plus 10,000 bytes, right? So our malloc has allocated 14,000 bytes. So that's the size of our actual heap. But the actual space needed to store our entire heap is going to be not 1,400 bytes if we need to put all of our heap in RAM at once, but it has to be the largest or the smallest page large enough to contain at least 14,000 bytes. So I think we actually need 4 pages, or 4 kilobytes times 4, which is 16 kilobytes of data to store it in RAM. Yeah? No, so you can just continue that stack. Because it's just one process, so we can just stick, right after a malloc of 4,000, we can start the malloc of 10,000. There's no reason we have to skip to the next page boundary. Exactly. There may be some metadata that malloc has to use to figure out that you have those separate allocations. So it may take up slightly more space. But if you have no extra metadata, it would be exactly 4,000 bytes. So hopefully this gives you an idea of how memory actually works inside your computer, how we organize it, how different processes can share memory, and how all of this actually happens where we have thousands of programs running on some computers, all seamlessly accessing the same one physical block of RAM. So this is super cool. This is why I love computer science. It's like this is such a novel idea that just works so elegantly that now all of you understand. Cool. Any questions? Yeah. Oh, this actually leads directly into the start of lecture 5, actually, or lecture 6. So if I change out to the other sheet, we have basically where we ended up slightly. I think I designed it slightly differently, but we might have this potential memory layout in our system. So same program, same disk. And let's say we access, so here we've got pointers over to disk. These are pointing directly to disk. These are pointing to here. And then this is pointing over to disk here. So we've got a bunch of data pointing to different places. And now we access something that, has that page ever been allocated to our process yet? The big bold block. Does that have an entry in our page table? No. So it points to nowhere. What happens as a programmer when you access memory beyond the region you've allocated? You've probably done this in 225 a million times. Segmentation fault, a seg fault. So this is exactly the process that causes a seg fault. So if you access barely over your buffer, if you access like 1 character past the end of what you've allocated, you probably don't seg fault. Because if you just go a little bit beyond the memory, Valgrind should give you an error, because Valgrind will detect it, but you won't seg fault because you haven't actually gone on to another page. A segmentation fault only occurs as soon as you access another page. So this is the exact mechanism that you've seen happen on your programs probably hundreds of times. I know I've probably sig faulted like 10,000 times in my life. So this is what's happening. You're accessing a region of memory in your virtual address space that's not part of your page table. And for this reason, we also never put anything in address 0 in our page table. So you'll know in every single example, I'm never going to have 0 filled up in my page table. Because as operating system designers, we decided that we're going to never put something in 0 so that null always sig faults. So if you ever try and dereference a pointer null, and that's part of the reason you always try and set something you free to null, so if you do access it, you don't get garbage data, instead you get a sig fault. So this is what caused this sig fault. This is something that you've seen happen, and this is the understanding of how it actually happens inside of your operating system. Your operating system says, hey, you can't do that. We're going to kill your process through a sig fault. So, bold entry causes a sig fault. The next thing I want to talk about is just really quickly going over something that I think is useful to understand how the operating system decides it, and something that's useful to kind of get a feeling around how operating systems actually use this, which is the page eviction and replacement. So what we've done so far is we've talked about a number of different pages, and I want to know, how do I determine which page should get removed given a series of page access patterns? So let's say we have a bunch of page accesses, that we might first access page 17, then page 33. So we have different strategies, and the first strategy I want to look at is the optimal strategy. So strategy number 1 is called OPT, or optimal. And this looks ahead to see what page is not used furthest until furthest in the future. So the optimal page replacement strategy is I'm going to look ahead at all of my memory allocations when I have to evict a page and determine what page is not used for the furthest time in the future. So if I go ahead and go through this period of allocations, I'm going to say the first thing I do is I need to access page number 17 in my CPU. So I need to load 17 into RAM. I might just go ahead and put it in RAM 0. There's nothing there. Second allocation, 17 is still in RAM 0, but I can go ahead and put 33 in RAM 1. Third allocation, 40, well, it's RAM 0 is still taken up, so I can go ahead and put 40 inside of RAM spot 2. And now 17 gets accessed again. 17 is already in RAM, so we don't even need to load anything new in RAM, right? So we can access just at page 0. 33 still stays in RAM, 40 stays in RAM. 43 is a new access, so we can go ahead and put 43 in the last slot of RAM. And all of the other things are in RAM still. Now we need to access page number 8. Is there any free spots in RAM right now? No. So because there's no free spots in RAM, we're going to have to kick something out. But before I do that, I want to mention one thing, which is where this page 17, if it's not in RAM, where is it almost certainly? If something's not pointing to in RAM, it's probably pointed to on disk. And whenever we have to load something new in RAM, I'm actually going to put a box around it, because this is what we call a page fault. So a page fault occurs when a data is not already in RAM, and we need to move it into RAM. So a page fault occurs here at 17. A page fault occurred here at 33. A page fault occurred here at 40. A page fault occurred here at 43. So page faults take time. They require us to copy data. We don't like page faults. We want to minimize them. So the idea here is we want to minimize page faults. So what we want to do is we want to say, okay, memory address 8, we're going to look into the future and see which memory is least used for, or not used until furthest in the future. So we don't want to cause a page fault. So we can look at 17 and we can say, is 17 going to be used again? Yeah, it's going to be used in about 5 time units. Is 33 going to be used again? Yeah, it's going to be used in about 3 time units. Is 40 going to be used again? No. So 40 is something we can remove. Is 43 going to be used again? No. Which one do we want to kick out? 40? Why 40? Yeah, why? Oh, we could be lazy and not even check for 40. Yeah, that's one reason. Another reason might be it's the least recent, or it's like the furthest least recently used. So 43 was just recently used, or just recently added. So we could use some like least recently used tiebreaker. That's usually the tiebreaker we end up using, is what was least recently used. So yeah, I agree. It sounds like 40 is a great thing to kick out of RAM. So we're going to go ahead and page fault and put 8 into RAM where 40 was. And now 99 happened. 99. What do we kick out, given a least recently used tie break? 43, yeah. So 99 gets loaded in. Now we access 33. 33 is already in RAM. We don't need to page fault. So that is great. 99 is already in RAM. We don't need to page fault. And 17 is already in RAM, so we don't need to page fault. So this is how page eviction ends up working. We have different strategies of how we want to do page eviction. So I'm going to say in the optimal algorithm, we had 6 page faults. And this allows us to compare how good different strategies are. But there's one serious problem in actually having optimal work in real life. Why does optimal not actually work? Yeah. Yeah, it has to see into the future. How do you know which if statement that program's going to take? How do you know what function it's going to call? How do you actually know in the future of what it's going to do? So optimal is the very best we can do, knowing what happened. So we're going to compare optimal versus all of our other strategies. So one second strategy we might use is a strategy we actually use for the tie breaks. This idea is we could just use a least recently used, or an LRU strategy. That we're going to evict a page that was least recently used. So the beginning happens the same. We go 17, that's a page fault. 33 is a page fault. 40 is a page fault. We access 17. And now 43 can get loaded into RAM as a page fault. Then we get to 8. And at this point, what page was least recently used when we got to the 8? 33. Ooh, we're not optimal anymore, but we have to use some heuristic that we can actually do something with. So yeah, we go ahead and kick out 33, because that was the least recently used page. And now 99, same idea. What's the least recently used page at 99 since it's not in RAM? What do we evict? We evict 40. Stick 99 in there. All right, 33. Least recently used? 17, yeah. 33 goes into the first part of RAM. 99 is already in RAM, so we don't need to evict anything. But 17 is not in RAM. When we reach it at the very end, what's the least recently used page? 43. So yeah, we go ahead and evict page 3 from RAM. So now if I count up my square boxes where I have these page faults where I have to load in data, here in this least recent use strategy, I have 8 page faults. So we can see it's less good than our optimal strategy, but still not terrible. And there's a number of different other strategies. A third strategy is least frequently used, or LFU. So least frequently used says we're going to actually keep track of a usage counter. And the idea here is that maybe there's some variable we access quite a bit over time. And if we have a tie, we're going to tie break with least recently used. So least frequently used, and if a tie of multiple things that were least frequently used, we're going to look at the least recently used one. So going through the same thing, we know 17 page faults into the first one, 33 page faults into the second page RAM, 40 page faults, we access 17, we page fault 43, and we have our first eviction when we access page 8. So what's the least frequently used? What are all of our candidates for least frequently used? 33 and 40 and 43, right? And then what's the least frequently used among those? So these each have one use. So of all of these that have one use, the least recently used one was 33, so we go ahead and kick it out, load in 8. And now here we're doing something different. So 99 is our next eviction. What do we evict here with least frequently used? 40, yeah. So 40 has only been used once, 43 has only been used once, and 8 has only been used once. But 17 has been used twice. So because 17 was used multiple times, we're going to be more hesitant to evict it. So we can go ahead and evict 40 here and put 99 in its place. Then we need to evict something for 33. What do we evict to place 33 into memory? We evict 43 because it's tied between all the one uses. 33 gets put in here. 99 is already in memory, and 17 is already in memory. So now counting up the boxes, here we have 7 page faults. And I want to go through just one more simple scheme with you that kind of combines one of the shortcomings of least recently used is there is a potential for starvation here. As soon as one page gets a whole bunch of uses, it essentially is the king or the queen of memory. Its counter is at 1,000. No one's going to get to 1,000 because other things are getting evicted. So there's a starvation problem that happens with least frequently used. But we like the fact it looks better than least recently used. It did better than LRU. It only has 7 page faults compared to 8. So the hybrid approach, and the approach that's used on modern systems, is an approach called not recently used, or NRU. So NRU has a recently used bit set to 1 when used. So we have a recently used bit that's set to 1 when it's used. And then we evict the least recently used page with RU is equal to 0. And if this is not possible, if no RUs are equal to 0, set all pages RU equal to 0. So the idea when it comes into memory, it has its recently used bit set to true. And then over time, eventually we're going to have to evict a page. We set all of their recently used bits to 0. And then as they get used again, their bits are going to get updated to 1. So you don't get to keep a counter forever, but as you get used, you keep getting to set your counter again to 1 and 1 and 1. So I think that's the only thing. Yeah, set it to 1 when it's used. So every time we use it, we get to reset it to 1. Only when we have to evict something and we have nothing to evict do we set all the 1s to 0. So pretty simple algorithm. And what's beautiful about this is we only need 1 bit. We just have a single recently used bit, and that bit controls everything. So again, going through this example, 17 page fault, 33 page fault, 40 page faults, 17's already here, 43 page faults. These all right now have their bits set to 1. So I need to evict something. They all have their bits set to 1. So because there's nothing that's set to 0, I'm going to go ahead and set all of them to 0. And then go ahead and evict the oldest page. What page am I evicting? Not 33. Sorry, it is 33. Yeah, not 17. Right? Because 17 was used more frequently than 33. Does that make sense? Oh, yeah. Well, I heard, like, I don't know. Yes, so 33 is definitely, because it's the least recently used. So go ahead and evict 33 and put 8 in its place, and that is a page fault. And now 8 has its bit set to 1. All the other bits are set to 0. So now we need to load 99 into memory. 99, where does it go? We have 3 candidates. It can be either 17, 40, or 43, because those are the bits that are set to 0. And the oldest of those 3 candidates is 40. Yep, so 99 goes here. Its bit is set to 1. And then 33 is access. Unfortunately, 33 is not in memory. So of the 2 candidates that have their bit set to 0, which one do we evict? 17 now, right? Because 43 was used more recently than 17. So 17 was the least recently used thing that has its bit set to 0. So if 17 got used a little bit more frequently, it would have stuck in there. But because it wasn't used for a long time, even though it's pretty frequently used, this most frequently used, or sorry, this not recently used algorithm is not helping 17 out. So that bit's now set to 1. Stop. There we go. So that bit's set to 1. 99 is already in memory. That bit gets set to 1. Then we have our final eviction. And our final eviction happens to put 17 in memory. Where do we need to put 17 in memory? We look at the only thing that has its bit set to 0, so there's not really a decision. We put 17 down here. So we have 8 page faults. So not recently used is an approach that sort of combines the idea of least frequently used and not recently used into a single algorithm. And it does it by having just a single bit that we switch to on and off as we look through the pages to evict. So every time we need to load a new page into memory from our page table, when we have to get that into the CPU, we're going to go ahead and use that bit. So there's a number of other different strategies that sometimes are used. So sometimes there's strategies like most frequently used, which is kind of a weird strategy. There's this idea of a working set, where the working set is this idea that we have a per process memory allocation, eviction. So there's a few other terms that you might see around when you're talking about them, but the main 4 ideas we've gone over through the 4 examples. So I want to go through one, I want to go through one quick example real fast. and really connect this to heap and stack memory to begin to really think about the next MP. So with heap and stack memory, you know from your time in 225 that you have two different types of memory, that you have heap memory and you have stack memory. And in that different types of memory, what is heap memory? What gives us heap memory in 225's time? New? Is that what you said? Yeah. Yeah, new gives us heap memory. And what's in our stack memory? Yeah, everything that's kind of just automatically managed, so automatic variables, everything that's not used by new or not used by malloc is sort of just stack memory. And stack memory, if we run this program, what do we expect the stack memory addresses to be? Do you remember from 225? What do you expect stack memory addresses to be? Where does it live in memory? You have a different question, or do you use stack memory? Yeah.
I feel like the way you described it is actually identical to $u, and maybe you meant the hybrid with FRU instead of $u.
Oh, we can talk more after that, after class, but it is slightly different because we do have that bit. But in stack memory, if we think about our heap is one big chunk of memory, and our stack memory is always going to live at high addresses. So stack memory lives at high addresses, and stack grows down. So if we look at the memory address of the output of any program, when we have a stack address, it's going to be a very, very large address. And heap addresses are small addresses. And heaps grow up. So in our virtual memory space, we're going to start our stack off at a very, very high virtual address. So if we look at our entire virtual memory, we're going to start our stack address with a whole bunch of like high numbers, and then as we allocate more memory, we're actually going to grow the stack down. As we allocate heap memory, heap addresses are going to be very small addresses relatively. They might only be 8 or 9 digits instead of 14 digits. They're going to have a lot of zeros in front of them. They're going to be very low addresses and grow up. And we run out of RAM in our process when our virtual page table stack pointer of where our stack is and our heap pointer meets in the middle. So when our stack reaches the heap, we meet in the middle. We're out of memory. So our virtual page table is going to be limited in size. There's going to be some amount of space that we can't malloc any more memory. But we can identify what's a heap memory address and what's a stack memory address. And what I want, so for MP3, what you're going to do is you are going to take a program and you are going to actually write the malloc implementation. And I've set it up so that you actually sideload malloc into the real Linux kernel, so that you're actually able to use your malloc on any program in the system as long as it's a single-threaded program. So you're going to actually get a program malloc. And what you're going to do is you are going to know that the initial heap size is 0 bytes. I'm just jumping to the last part. And you only have to learn one new system call for MP3. And that is sbreak. Sbreak increases the size of your heap. So the beginning of your heap is 0. After you call sbreak, your operating system is going to extend the heap for you so you have more information. So when you run a program, I've actually set up this program in MP3. So in MP3, you're going to see this exact same code. And what I want you to do is before Tuesday, get started just enough. So in MP3, I give you a simple malloc implementation. I give you a malloc that you'll actually see what's going on. I've drawn a bunch of different diagrams. And what I want you to do before Tuesday's lecture is at least get started on MP3 to print out what your stack is. So you can see how MP3 stack actually works and see how the stack grows and see the pointers on the stack, or on your heap, sorry, on your heap. So get started on MP3 before Tuesday's lecture, because I'm gonna go through the exact example that you're working with in your MP3 code, and we're gonna finish up this sheet by actually seeing how this actually works in RAM. And if you've started MP3, you will actually experience this yourself through programming. So you'll be able to see how what you've programmed matches up to see what you in this code. So you'll see this exact code in MP3, and this is where I want to start off on Tuesday, so you can see what you're doing in your MP here in lecture, and see how everything you're doing combines and meets the same. And we'll talk about strategies on how to optimize MP3 on Tuesday. So have an amazing weekend. I'll be here for a few minutes if you have any questions. Otherwise, good luck on finishing up MP2 and homework 2. They're both due tomorrow. See you next week.